Section 16.2 is the rational zeros of a polynomial function. And I would just remind us about a rational number is a number that can be written as P over Q, where P and Q are integers. So just a little reminder, all the numbers on the number line are the real numbers. So the number line represents all of the real numbers. Then if you talk about the tick marks on the number line, those are the integers. So the positive counting numbers, 0, and the opposite of all the positive counting numbers. And so any number that can be written as -1 over 2, an integer over an integer, or 3 over 4, or if it can be written as 6 over 1, integer over an integer, those are all rational numbers. And if you put a rational number in your calculator and do the division problem, 1 divided by 3, you get 0.33333, and 3's fill up your screen. If you put 1/9, you'll see that 0.1111 ones fill up your screen. Rational numbers either fill up the screen with digits that have a pattern to them, a repeating pattern, or they end, like 3/4 just equals 0.75, has 2 decimal places, and then it ends. So every rational number either is a repeating decimal or a decimal that ends. And any number that's not a rational number is called an irrational number. So I want to make sure we know what we're talking about here, where we're talking about rational zeros. So we're not talking about something like 3/4 plus or minus the square root of 17 over 4, because this is irrational. And you already know how to find zeros like this using the quadratic formula. So we're talking about rational zeros only in this entire section. So we're going to learn the factor theorem, the rational zero theorem, then we're going to work on finding rational zeros. So I want to keep reminding you about these 4 equivalent statements. It's like 4 for the price of 1. If you know any one of these things, then you know all 4 of these things. So suppose 4 is a real zero of your polynomial function. Then number 2 tells us the 0.40 is an x-intercept of the graph of the polynomial. Then we also know that x minus 4 is a factor of f, which means it divides evenly into it with no remainder. And then we also know that 4 is a solution to the equation f of x equals 0, or another way of saying that is f of 4 equals 0. So if you know any one of these things, you know all 4 of these things. And we're going to keep encouraging you to remember that you know a lot more things than you might think if we give you one of these items. So let's talk about the factor theorem. It says if f of c equals 0, then x minus c is a factor of your function. And if x minus c is a factor, then c is a 0. So if you know one of these, you know the other. So in this example, we're going to use the factor theorem to decide whether x minus c is a factor of f. So we're going to ask the equivalent question, is f of c equal 0? Because that's the same thing as saying x minus c is a factor. Well, we figured out using the remainder theorem that if we do synthetic division, and if we have x minus 2 we're dividing by, and we put a 2 in the synthetic division, then the number we get here for the remainder is f of 2. And so if we get 0, we can conclude that x minus 2 is a factor. So remember when you're using synthetic division that you have to have placeholder zeros for any degree term that's missing. So we have a 4 for the degree 4 term, no degree 3 term, so we need a 0. Negative 15 for the degree 2 term, 0 for the x term, and then negative 4. So the 4 comes down. 2 times 4 is 8. Add and you get 8. 2 times 8 is 16. Add and you get 1. 2 times 1 is 2. Add and you get 2. 2 times 2 is 4. Add and you get 0. So we can conclude x minus 2 is a factor of f. And in fact, if we look at the depressed equation represented by the last row of numbers besides the remainder, the 2 is the constant, 1 is the x coefficient, 8 is the x squared coefficient, and 4 is the x cubed coefficient. What we've just figured out is that 4x to the 4th minus 15x squared minus 4 can be factored to x minus 2 and 4x cubed plus 8x squared plus x plus 2. So make sure you're paying attention to all the things that you learn by doing one simple synthetic division. You've learned a lot. Okay, so the number of real zeros, if we have a polynomial function, it can't have more real zeros than its degree. So that tells you how many to possibly look for. If you have degree 5 and you find 5 zeros, then you should stop because you have found them all. And when we're counting zeros, we count each zero as many times as its multiplicity. So if we have x minus 2 cubed, so suppose our function could be factored like this, and x plus 3 squared, and x minus 4 to the 5th, then we'd say x equals 2 is a 0 with multiplicity 3. And x equals negative 3 is a 0 with multiplicity 2. And x equals 4 is a 0 with multiplicity 5. So this is a degree 10 polynomial, and it has 10 zeros because we count each zero by its multiplicity. Okay, so now we need the rational zeros theorem, and any generic polynomial can be written in the form where we have the highest degree term is x to the power of n, and then we name its coefficient a sub n. Then you would have the next degree down and the next degree down until you got to the linear term and then the constant. So every polynomial doesn't have all of those terms. We just looked at a polynomial that was missing some of the terms. But you're definitely going to have an a sub n because that's the highest degree term. So you also might have a constant or it might be 0. But if you have some number p over q and it's reduced down as much as possible, it's in lowest terms. If it's a rational 0 of the function, then p must be a factor of the constant, a sub 0, and q must be a factor of the leading coefficient. So if there exist rational zeros, they must be in the form a factor of a sub 0 over a factor of a sub n. So that's if rational zeros exist. We already talked about if your only zeros are 3 plus or minus the square root of 17 over 4, these are two irrational zeros, and this theorem is not going to find them. It says if there are rational zeros, then they will have to be on this list of factors of a sub 0 over factors of a sub n. So let's look at an example. And this example just says to list the potential rational zeros. Just make a complete list of all the possible rational zeros without attempting to find them. So we know if there is a rational zero, will have to be a factor of 2 over a factor of 6. So let's make a complete list of those. And you have to think about that 2 can be written as either 1 times 2 or negative 1 times negative 2. So plus and minus 1 and plus and minus 2 are all the factors of 2. Okay, 6 has more. 6 has 1 times 6, negative 1 times negative 6, 2 times 3, and negative 2 times negative 3. So the way I show this to myself is I just say I know my numerator either has to be positive or negative 1 or positive or negative 2, and my denominator has to be positive or negative 1, 2, 3, or 6. This is just my shorthand way of saying here's all the possibilities, but you are being asked to make a list, so you need to actually make a list. So we say, well, 1 over 1 and 1 over negative 1, positive or negative 1, could be a potential zero of this function. We don't know if it is or not. We're not trying them, we're not testing them, we're not worrying whether they are or not, we're just worrying about making a list. So then I have plus or minus 1 over 2, so plus or minus a half. Then I have plus or minus a third, and plus or minus 1/6. Then if I put 2 over 1, I'm going to get plus or minus 2. But see how 2 over 2 doesn't give me anything new. But 2 over 3 gives me another pair of possible rational zeros. But then 2 over 6, I already have that. So this is the complete list of possible rational zeros. So let me say this again. It's if this polynomial does have a rational zero, it has to be on this list. So this list gives you a place to start testing numbers to see if they are rational zeros. If you run through this entire list and none of them work, then this function does not have a rational zero. Okay, it's conclusive. This list is complete. If you try every single one and none of them work, this function does not have a rational zero. Okay, it might have a pair of complex conjugate zeros and a pair of irrational zeros. Okay, so let's do the same thing for b, where we know we'll have factors of 10 in the numerator, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, over, have a 6 in the as the leading term, so plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So we can make our complete list. 1 over 1 is 1. 1 over 2 is a half. 1 over 3 is a third. 1 over 6. And then we have 2 over 1, but 2 over 2 we already have. 2 over 3, 2 over 6 we already have. plus or minus 5, plus or minus 5 halves, plus or minus 5 thirds, plus or minus 5 sixths, plus or minus 10, but I already have plus or minus 5, plus or minus 10 thirds, and then 10 sixths would be 5 thirds, so I already have that one. So this is the complete list. So I'm going to pause here and come back and do a second part to the video where we're going to actually find some rational zeros.